Welcome to the deep dive. We've got something really intriguing lined up for you today. Forget scrolling through articles, we're getting hands-on, in a way. By exploring the Pythabacus, we've been looking at demonstrations of how this incredible tool uses the movement of beads to actually show multiplication.
Yeah, it's quite visual.
It really is. But what we're really going to dig into today is how this tactile experience, touching the beads, connects with some pretty fundamental mathematical ideas, the concepts of sets and groups.
Exactly. We've been looking at these transcripts from YouTube videos where people demonstrate the Pythabacus for multiplication. And what's particularly fascinating, I think, is how the physical act,
Moving the beads?
yeah, moving the beads, it mirrors the abstract logic of sets and groups.
Yeah.
Gives us a very concrete way to understand things like inner and outer products, which can be quite abstract otherwise.
Okay, so let's start simple then. Let's imagine multiplying, say, 4 by 3 on the Pythabacus. You push 4 beads across on one post, right? And then you kind of mark 3 on the other. Visually, you end up with this rectangle formed by the beads between those 2 points.
And that's key. As one of the demonstrations points out, there will always be a rectangle between any two triangles that has a number of beads equal to the product of the beads on the base of the triangles.
Right, so for 4 by 3, that rectangle has 12 beads. Simple as that.
It's a direct visual representation of the product, 12. So even with this basic rectangle, how does that start to hint at maybe combining elements from two different sets?
That's a great question. It's sort of like the 4 beads represent one collection, one set maybe, and the 3 represent another set. And the rectangle, well, it shows us all the possible pairings you could make if you took one bead from the first set and paired it with one from the second set.
Precisely. That's really the essence of what we'll later see described as the outer product of sets.
Yeah.
It's about those combinations. Now, things get a little more involved when we multiply numbers where the sum is greater than the initial number of beads on the base. Usually that's 10 in the early examples we saw.
Ah, right. Like 6 times 8.
Exactly. 6 times 8. You move 6 beads across. But then when you need to count the 8, you only have 4 more beads left on that first side before you hit the end, the base of 10.
Right, you run out. So the demonstrations show you continue counting on the opposite side using beads that were already moved for the first number. And what's interesting there is that those beads, the ones that were part of both counts, the 4 overlapping ones in the 6 by 8 case, they seem to take on an extra value. It's related to that base of 10.
Yes, they contribute 4 times 10 or 40 to the total.
And the remaining beads in that final rectangle, the ones that weren't part of the overlap, they give you the other part of the answer.
Such as 8 in the 6 by 8 example. So you have the 40 from the overlap plus the 8 from the final rectangle.
Gives you 48. It's like that base 10 structure is physically embedded in how you have to move and count the beads when you run out.
That's a really key insight, I think. The physical constraint, reaching the end of the base and then continuing the count, it forces you to represent numbers in a way that actually mirrors our base 10 system or whatever base you're using.
Okay, so what about factors that are larger than the base? Like, say, 12 multiplied by 4, still using that initial base of 10 for now.
Right, so to represent 12, you first count the 10 beads on the base. Then you have to loop back, sort of, and count 2 more on the same side. So those 12 beads are now marked or moved.
Okay, got it. 12 is 10 plus 2.
Then, when you multiply by 4, as the demonstration shows for 12 by 4, you effectively have 4 groups of 10 represented within the base structure that's 40.
Okay.
Plus, you have those extra 2 beads, the ones that made 12 into 12 instead of 10, also being counted 4 times. So that's 2 times 4, which is 8.
Right, so you get 10 plus 10 plus 10 plus 10, that's the 40,
Right.
plus the 8 from the extra bits, 48.
Precisely. 12 by 4 equals 48. Now, here's where the connection to sets and groups starts getting really explicit in the sources we looked at.
Okay.
The demonstrations start talking about each bead you touch as representing an element in a group within a larger set.
Ah, so we're moving from just counting to thinking about the beads as actual members of categories.
Kind of, yeah. Think of each column on the Pythabacus, maybe each post, as representing a distinct group. And when you move a bead, you're selecting an element for that group.
Okay, that makes sense.
And then there's this idea of assigning a numeral to the elements. This lets you create subsets within those main groups. Like you could label some beads you count as type 1 and others as type 2.
So if I count, say, 3 beads across, and I decide these are my numeral 1 elements,
Mm-hmm.
and then I count 5 more and call them numeral 2 elements. I've essentially created 2 different subsets, right? One of size 3, one of size 5 within that column or group.
Exactly. You've defined 2 subsets. Now think about multiplication again, but through this lens, this is where the idea of the outer product comes in really beautifully.
Okay.
Multiplication on the Pythabacus, when you look at it this way, is like finding all the possible unique pairings you can make by taking one element from your first set and one element from your second set.
So going back to our earlier simple example, the 4x3. The 4 beads are set 1, the 3 beads are set 2, the 12 beads in the rectangle.
They represent the 12 unique pairs you can form, one from the set of 4, one from the set of 3.
Got it. So if I have my set of 3 numeral 1 beads and my set of 5 numeral 2 beads, and I multiply 3 by 5,
Right.
the 15 beads that appear in that resulting rectangle, they visually represent all 15 possible pairings I can create. It's like the physical arrangement is the combination of elements across sets.
Precisely. And the demonstration actually says it quite clearly.
Yeah.
How many pairs of 1 and 2 can I make unique pairs are possible between these sets of elements? And we will see that that would be the product we call the outer product of 3 times 5, which will equal 15.
Wow. Okay. That connects the physical action directly to the abstract math concept.
It really does. Now, things get even more interesting when we consider something called inner products.
Inner products. Okay, how does that fit in?
So we have these subsets defined by our numerals, the type 1s and type 2s.
Mm-hmm.
The inner product in this context refers to pairs of elements that have the same numeral within their respective groups or positions defined by the base. It's about the matches within our sets based on that shared characteristic, that numeral.
Okay, so outer product is pairs between different types, 1 and 2. Inner product is pairs of the same type, 1 and 1 or 2 and 2.
Essentially, yes, related to how they align within the base structure. And to really see how this works, the demonstrations sometimes shift away from base 10. They might use, say, base 8.
Changing the base. So instead of 10 beads making a full set, it's 8.
Exactly. The base, as we're seeing, acts as a kind of cycle or limit in our counting. Once you count 8 beads, the count sort of resets or moves to the next level or extension.
So how does this base, like base 8, relate to these inner and outer products during multiplication?
Let's take an example from the source, multiplying 3 by 7 in base 8. Suppose, just hypothetically, when we set this up, we end up with a situation where our outer product calculation, pairs of numeral 1 with numeral 2, give us 5.
Okay, 5 pairs of different types.
Now, because we're working in base 8 and multiplying 3 by 7, we also look at the inner product combinations pairs of the same numeral aligned within the base 8 structure. Let's say there are 2 such combinations in this example.
2 matches.
2 matches, yeah. The demonstration states that the multiple of base 8 is the sum of the inner products times 8.
So the base number multiplies the inner product count.
Correct. So with 2 inner product combinations, that's 2 times the base. 2 by 8 equals 16.
Okay.
Then you have the outer product we found earlier, which was 5. So 16 plus 5 gives us 21.
And 3 times 7 is 21. Wow. So the Pythabacus, especially by using a different base, visually separates out these contributions, the inner product contribution, scaled by the base, and the outer product contribution.
That seems to be exactly the idea presented. And it goes further. Continuing the count beyond the base, like past 8 in this case, seems to create what the sources call extensions of groups.
Extensions, like when we did 12 in base 10, that was 10 plus an extension of 2.
Precisely. So if we multiply, say, 3 by 11 using base 8, 11 is 8 plus 3. So you get a full group of 8 and then an extension of 3 beads.
Okay.
Depending on how the numerals are assigned, you might end up with extensions associated with numeral 1 and numeral 2. Let's say in this 3 by 11 example, we end up with 2 extensions, each of size 3.
Right. One for each numeral type, maybe?
Could be. The outer product calculation then also applies to these extensions. The product of their sizes, 3 by 3 equals 9.
So another outer product, but this time for the parts that went beyond the base.
Exactly. And this outer product of the extensions, 9, is added to the contribution from the inner products multiplied by the base. If we had, say, 3 relevant inner product combinations within the base structure, that's 3 by 8 equals 24.
Okay, 24 from inner products times base.
Plus 9 from the outer product of the extensions.
Is 33, which is 3 times 11. It works.
It does. And the source summarizes it neatly. You can understand the multiplication on the Pythagoras as being equivalent to the inner and outer products of groups of elements from 2 subsets. In this case, we can see defined by the numerals 1 and 2.
That's a really powerful way to connect the physical manipulation to the underlying math. So finally, the demonstrations also revisited that scenario where the first factor is larger than the base.
Yes, like 13, using base 8 again.
So 13 and base 8 is one group of 8 plus an extension of 5.
Correct. That initial count sets up the base group and the extension. When you then multiply, say, 13 by 2, you're looking at the inner products related to the base group structure, perhaps giving you, say, 2 combinations times the base. 2 by 8 equals 16. And then you also calculate the outer products involving that extension of 5. So multiplying by 2 means you take that extension size, 5 times the multiplier 2, giving 10.
So 16 from the inner product times base part plus 10 from the outer product involving the extension part. That's 26. 13 by 2 equals 26.
So that structure holds even if the numbers get bigger. It's always breaking down into contributions from inner products scaled by the base and outer products, either between base groups extensions or between extensions themselves.
So when we look at the Pythabacus, it's really not just a calculator, is it? It's, well, the very act of touching and moving these beads gives you this tangible visual handle, how they interact through inner and outer products when you do something like multiplication.
Absolutely. The beads stop being just passive counters. They start to embody the elements within these defined sets and groups. And by following the rules of moving them on the Pythabacus, you're physically enacting operations on these sets, and you see the mathematical outcomes, like the product, made completely concrete right there in front of you.
It really makes you reconsider how we often think about abstract math as something totally separate from the physical world, doesn't it?
It does.
Makes you wonder what other physical tools, or maybe even just everyday objects around us, could be hiding similar connections. You know, connections to fundamental mathematical structures like sets and operations, if only we looked at them in the right way.
That's a fascinating thought. What else could be a tangible representation of abstract math?
Yeah, something for you to think about until our next deep dive.